Separable differential equation. This is the main focus of this video lesson. We will also try to solve the general and particular solutions of this kind of equation. As the name implies, differential equations are equations that involve differentials. In other words, these are equations containing an unknown function and its derivative. A differential equation is said to be separable if you can write it in such a way that each side of the equation involves only one variable. Separable differential equations can be written in the form f of y dy equals g of x dx. Observe here that on the left, only y variables can be seen, and all x variables are situated on the right. With that, variables are distinctly separated together with their corresponding derivatives. Hence, we call them separable differential equations. Now, we will determine if the given differential equation is separable or not, and to rewrite it in the general form if it is separable. Take note that the general form of our separable differential equation is in the form f of y dy equals g of x dx. In rewriting separable differential equation, we will only apply the multiplication property of equality. Our first target is to combine all the y variables on the left and the x variables on the right. To do that, we will multiply both sides by dx. We have dx dy over dx equals y squared x squared dx. On the left, after cancelling the dx, the equation now becomes dy equals y squared x squared dx. Next, we will find ways so that the y squared on the right will be transferred to the left. We can do that by multiplying both sides by 1 over y squared. After multiplying both sides by 1 over y squared, our equation becomes 1 dy over y squared equals y squared x squared over y squared dx. Observe now that on the right side of the equation, we can cancel y squared. So the equation becomes dy over y squared equals x squared dx. Since each side of the equation involves only one variable, then it is separable differential equation. In this given, we can rewrite the equation by applying the cross multiplication. Cos y dy equals sin x dx. Take note that all the y variable are on the left and all the x variable are on the right. Therefore, we can say that this is a separable differential equation. For the third given, we will multiply both sides by dx. Dx times dy over dx is dy, and dx times 12x squared minus 4y plus 2 is 12x squared minus 4y plus 2 dx. Since there is one y variable on the right side of the equation, therefore this equation is not considered as a separable differential equation. To solve the general solution on separable differential equation, let us consider first this equation. Dy over dx equals x squared is a separable differential equation. We can integrate both sides, taking extra quotient with the constants of integrations. For y variable, we will use c sub 1 for the constant and c sub 2 for the constant for x variable. The integral of dy equals the integral of x squared dx. The integral of dy is the same as y plus c sub 1. And the integral of x squared dx is equal to x power 2 plus 1 over 2 plus 1 plus c sub 2. The equation becomes y plus c sub 1 equals x cubed over 3 plus c sub 2. Getting the additive inverse of c sub 1, the equation becomes y equals x cubed over 3 plus c sub 2 minus c sub 1. Since c sub 1 and c sub 2 are arbitrary constants, and both are elements of real number, then by closure property, the difference between c sub 2 and c sub 1 is also an element of real number. Now, we let another constant c equal c sub 2 minus c sub 1, where such c is also an element of real number. Since we let c equal c sub 2 minus c sub 1, the equation now becomes y equals x cubed over 3 plus c. This solution to the differential equation is called the general solution. It is general in the sense that it represents a family of solutions to the given differential equation. In other words, the constant c can be any number, and since it does not specify any particular number, then it is said to be general. We will now get the general solution of dy over dx equals y squared times x squared. The general form of this equation is y power negative 2 dy equals x squared dx. Now we will integrate both sides of the equation. The integral of y power negative 2 dy is equal to y power negative 2 plus 1 over negative 2 plus 1 plus c sub 1. And the integral of x squared dx is x power 2 plus 1 over 2 plus 1 plus c sub 2. For the left side of our equation, y power negative 2 plus 1 is y power negative 1 over negative 1 plus c sub 1. And y power negative 1 is the same as 1 over y. The reciprocal of negative 1 in the denominator is the same as negative 1 plus c sub 1. Multiplying 1 over y and negative 1, the product is negative 1 over y plus c sub 1. For the right side, x power 2 plus 1 is x cubed over 3 plus c sub 2. We will now get the additive inverse of c sub 1. Applying the additive inverse of c sub 1, the equation becomes negative 1 over y equals x cubed over 3 plus c sub 2 minus c sub 1. We will let c equal c sub 2 minus c sub 1, so the general solution of this equation is negative 1 over y equals x cubed over 3 plus c. For dy over dx equals sin x over cos y, to rewrite this into general form, we can apply the cross multiplication. So we have cos y dy equals sin x dx. Integrating both sides, so the integral of cos y dy according to the theorem is equal to sin y plus c sub 1. And the integral of sin x dx is negative cos x plus c sub 2. Additive inverse of c sub 1, we have sin y minus negative cos x plus c sub 2 minus c sub 1. We let c equals c sub 2 minus c sub 1. So the general solution of this differential equation is sin y equals negative cos x plus c. For this differential equation, xy cubed dx plus e power x squared dy equals 0, let us rewrite this into general form. To modify this equation, we will get the additive inverse of the second term. Xy cubed dx equals negative e power x squared dy. To spare the left side with the variable y, we will divide both sides by 1 over y cubed. 1 over y cubed times xy cubed dx is x dx. And 1 over y cubed times negative e power x squared dy, just copy that one. On the left, we have already the variable x. Our goal for the right side is to combine all the variable y. To omit the variable x on the right side, we will divide both sides by negative 1 over e power x squared. So the answer now becomes x times the negative 1 over e power x squared dx equals, multiplying this negative 1 over e power x squared and negative e over x squared, the product is 1. So for the right side, this is now in the form of 1 over y cubed dy. We can change the negative 1 over e power x squared into negative e power negative x squared. Multiplying x and the negative e power negative x squared, the product is negative x e power negative x squared dx. And on the right, 1 over y cubed is the same as y power negative 3 dy. So this is now the general form of our differential equation. The next step is to integrate both sides. Let us first integrate the complicated side, which is on the left. For the integral of negative x e power negative x squared dx, since the numerical coefficient of x is negative 1, we will get negative 1 outside the integral sign, or simply, the negative of the integral of x e power negative x squared dx. We will apply the chain rule by letting u equals negative x squared. So du over dx is negative 2x, and du is equal to negative 2x dx. The goal is to make an equation equivalent to x dx. So what we did, we just multiply both sides of du equals negative 2x dx by negative 1/2. So du times negative 1/2 is negative 1/2 du equals negative 2x dx times negative 1/2 is positive x dx. Take note also that the negative of the integral of x e power negative x squared dx is the same as negative of the integral of e power negative x squared times x dx. We apply the associative property of multiplication by regrouping x and dx. Our integral now becomes negative of the integral of e power u, since we let u equals negative x squared x dx. And we will now substitute the value of x dx, which is negative 1/2 du. So that becomes negative of the integral of e power u times negative 1/2 du. Taking out negative 1/2 as a constant, so we have negative times the negative 1/2 and the integral of e power u du. Negative and negative 1/2 is positive 1/2, e power u plus c. According to the theorem, the integral of e power u du is equal to e power u plus c. Plugging in the value of u, which is negative x squared. So the answer is 1/2 e power negative x squared plus c. And for the integral of y power negative 3 dy, this is equal to y power negative 2 over negative 2 plus c. We equate the integral of both sides, c sub 1 for the left side and c sub 2 for the right side. Getting the additive inverse of c sub 1, so we have 1/2 e power negative x squared equals y power negative 2 over negative 2 plus c sub 2 minus c sub 1. And we let c equals c sub 2 minus c sub 1. So the equation becomes 1/2 e power negative x squared equals y power negative 2 over negative 2 plus c. To simplify the fraction, we will multiply both sides by positive 2. 2 times 1/2 e power negative x squared is e power negative x squared. 2 times y power negative 2 over negative 2 is equal to negative y power negative 2, and 2 times c is 2c. Additive inverse of negative y power negative 2 is y power negative 2. Additive inverse of e power negative x squared is negative e power negative x squared. The equation becomes y power negative 2 equals negative of e power negative x squared plus 2c. Rearranging the term on the right, it is now equal to 2c minus e power negative x squared. We will now raise both sides by negative 1/2. Take note that y power negative 2 raised to negative 1/2 power is equal to y power 1, or simply y. And for the right side, the quantity 2c minus e power negative x squared, raising this to negative 1/2 power, has two roots, positive and negative. So the equation becomes y equals positive negative of the quantity 2c minus e power negative x squared raised to negative 1/2. And since 2c is an element of real number, or 2c qualifies for any constant, then we will assign 2c equals a. So the general solution of this equation is y equals positive negative of a minus e power negative x squared raised to negative 1/2 power. We will now find the general solution of 2y dx minus 3x dy equals 0. Let us first rewrite this into general form. We simply get the additive inverse of the second term. That becomes 2y dx equals positive 3x dy. to omit y on the left side by 1 over y. And that becomes 2 dx equals 3x dy over y. And to omit the x variable on the right by 1 over x, so we have 2 over x dx equals 3 over y dy. And 2 over x is the same as 2x power negative 1, and 3 over y is the same as 3 times y power negative 1. So we will now integrate both sides. For the left side, that is 2 ln absolute value of x plus c sub 1. And for the right side, 3 ln absolute value of y plus c sub 2. Additive inverse of c sub 1 is negative c sub 1. And we let c equal c sub 2 minus c sub 1. So the equation is 2 ln absolute value of x equals 3 ln absolute value of y plus c. To understand the next step, take note and recall that log 4 base 2 is 2. And 3 times log 4 base 2 is 3 times 2 equals 6. And this is equal to the expression log 4 raised to the third power base 2. Since 3 is the coefficient of log, we take 3 and make it as a power of positive 4. In the given 2 ln absolute value of x, we will make use of the coefficient 2 as a power of our absolute value of x. Our equation now is ln absolute value of x squared equals ln absolute value of y cubed plus c. Applying the additive inverse of positive c, we have ln absolute value of x squared minus c equals ln absolute value of y cubed. Recall also that 0 equals ln 1, and the automatic base of the natural logarithm is the Euler number. This 0 equals ln 1 base e, when written into an exponential form, is e power 0 equals 1. On the given, ln absolute value of x squared minus c equals ln absolute value of y cubed, we will let 0 the whole expression on the left side of our equation. And we will use the Euler number e as our base, and that 1 represent the absolute value of y cubed. Therefore, from this form, we have e power ln absolute value of x squared minus c equals absolute value of y cubed. We interchange the placement of our expression. On the left is the absolute value of y cubed, and on the right are the factors of e power ln absolute value of x squared minus c. For the first factor, since e and ln are inverses, we can cancel them, so the remainder is absolute value of x squared, copy e power negative c. And since e power negative c is any real number, then we will let a equals e power negative c. So our equation now is absolute value of y cubed equals a times the absolute value of x squared. Next, we will extract the cube root of both sides of the equation. So we have the cube root of the absolute value of y cubed equals the cube root of a and the cube root of the absolute value of x squared. The cube root of absolute value of y cubed is absolute value of y. Copy cube root of a, and rewriting cube root of absolute value of x squared into exponential is in the form absolute value of x power 2/3. Since a is any real number, then we will let another variable b equals the cube root of a. From the definition of the absolute value, we have two answers. It could be the positive or the negative. Omitting now the sign of the absolute value and using its definition, the general solution now is y equals the positive negative b x power 2/3. Go back to the previous example, dy over dx equals x squared. And the general solution is y equals x cubed over 3 plus c. If we replace c by a specific real number, for example c equals 1, so the equation becomes y equals x cubed over 3 plus 1. This equation is called a particular solution to dy over dx equals x squared. Find the particular solution of the differential equation dy over dx equals y squared x squared, in which y equals 1 and x equals 2. The general form of this equation is y power negative 2 dy equals x squared dx. For the second steps, we will integrate both sides to get the general solution of this equation. The general solution of this equation is negative 1 over y equals x cubed over 3 plus c. This time, we will compute for the value of c. By using the general solution, we will substitute y equals 1 and x equals 2. So we have negative 1 over 1 equals 2 cubed over 3 plus c. And negative 1 over 1 is negative 1, and 2 cubed is positive 8. So we have negative 1 equals 8 over 3 plus c. Multiplying both sides by 3, that becomes negative 3 equals 8 plus 3c. Additive inverse of 8 is negative 8. We have negative 11 equals 3c. To get the value of c, we will divide both sides by 3. Therefore, c is negative 11 over 3. We will now go back to the general solution and substituting c equals negative 11 over 3. So the particular solution of this equation is negative 1 over y equals x cubed over 3 minus 11 over 3. For the second given, find the particular solution of the differential equation dy over dx equals sin x over cos y, where y is 0 and x is pi over 2. For the first step, rewriting into general form by applying the cross multiplication, we have cos y dy equals sin x dx. The integral of cos y dy is equal to sin y plus c sub 1, and the integral of sin x dx is negative cos x plus c sub 2. Additive inverse of c sub 1, so we have sin y equals negative cos x plus c sub 2 minus c sub 1. And we will let c equal c sub 2 minus c sub 1. So the general solution is sin y equals negative cos x plus c. Since y is 0 and x is pi over 2, by substitution, the value of c is 0. Therefore, the particular solution of this differential equation is sin y equals negative cos x.